Hello everyone, today we are going to study the CPU interrupts. As we have studied earlier that once the CPU is powered on, by default it executes the sequence of instructions one after the another. The flow of the control is changed internally with the help of special branch instructions. These branch instructions either unconditionally changes the flow of control or the change of the flow of the control is based on the status of one of the flags in the command status register. The interrupt is another mechanism which changes the flow of control. The transfer of the program control takes place either by occurrence of an event internal to the processor hardware or an event in its external hardware. For example, when an external device like printer finishes the printing of the pages sent earlier, it makes the request for sending the new pages through an interrupt. When the processor receives the interrupt, it suspends its current operation and transfers the control to a special procedure or a subroutine. The job of that special procedure or subroutine is to serve the device. In case of printer, it may be sending few additional pages for printing to the printer. Instead of talking in general about the interrupts, it is better if it is understood taking an example of a typical microprocessor like 8088. Therefore, today we are going to study what is an interrupt, how it occurs, what happens in the CPU when it receives an interrupt, what are the different types of the interrupts. The basic concepts related to interrupts are explained using the example of a microprocessor like 8088. Also, the various applications of interrupt are explained in brief. An interrupt by its name is an interruption to the normal sequence of the execution of the instructions a CPU is currently working on. The interruption to the normal working indicates that CPU needs immediate attention to something more important. An interrupt alerts the processor to a higher priority condition requiring the interruption of the current code the processor is under execution. The interrupt to the CPU could be in the form of an external hardware signal. The external signal is activated and interrupts the CPU through a special interrupt pin of the CPU. The interrupt may also come through a software instruction. The processor responds by suspending its current activities and saving its state in the memory. The current value of all the registers inside the CPU represent the state of the CPU. These registers are saved on the stack and the program control is transferred to a small program called interrupt handler, also called interrupt service routine and called ISR in short. After the interrupt service routine finishes the execution by responding to the device, the processor resumes execution of the previous activities by restoring the saved state of the register. There are two types of interrupts, a hardware interrupt. An hardware interrupt is an electronic alerting signal sent to the processor from a device. The hardware interrupt signal is also referred to as an interrupt request called IRQ in short. The device may be internal to the computer like hard disk, disk controller, keyboard or a mouse device. Interrupt may also come from an external device like printer, scanner or any other device connected externally to the computer system. For example, pressing a key on the keyboard or moving a mouse sends a hardware interrupt signal that causes the processor to transfer the control to an interrupt service routine. The ISR is a routine which reads the keystroke or a mouse position and responds according to the keyboard stroke or a mouse position. The hardware interrupts are asynchronous and can occur in the middle of the instruction execution. However, the processor finishes the current instruction under execution and responds to the interrupt before the execution of the next instruction. So, this is about hardware interrupt. The next type of interrupt is a software interrupt. A software interrupt is initiated when an exceptional condition occurs in the processor itself or through a special instruction in the instruction set which causes an interrupt when it is executed. The exceptional condition occurs in the processor when there are errors during the instruction execution or events that cannot be handled by the program itself. For example, if a processor's arithmetic and logical unit, called ALU in short, because of some program's error is required to perform divide operation in which the denominator is 0 value. This impossible computation will generate an interrupt called divide by 0 exception. The exception will transfer the control to an interrupt service routine. The job of that interrupt service routine is to abandon the calculation and display an error message which corresponds to divide by 0 error. The software interrupt instructions function similar to subroutine calls. The only difference is that the interrupt instructions are shorter in size, the ISR locations are implied in the instructions and therefore are time efficient as well. Because of the time and space efficiency of the interrupt instructions as compared to subroutine calls, they are used for calling frequently used low level operating system functions. For example, computers often use software interrupt instructions to communicate with the disk controller to request data be read or returned to the disk. Each interrupt has its own interrupt handler. The number of hardware interrupts is limited by the number of interrupt request lines to the processor, but there may be hundreds of different software interrupts. Interrupt is a commonly used technique when the computers have to simultaneously handle multiple events and the nature of the events is asynchronous. That means they can occur any time. Through interrupts, a single processor system can be made capable of handling multiple tasks at a time. If the multiple tasks require timely response and a single processor speed is not enough, a system with multiple processors is suggested in a real time environment so as to handle large number of interrupts connected over large number of devices. Such a system is said to be interrupt driven. The 8088 microprocessor is capable of handling up to 256 interrupts. These interrupts are divided into 5 groups. The first group is external hardware interrupt. The second group is software interrupts. Third group is internal interrupt. Fourth group is non-maskable interrupt. And the final one, fifth group, has one interrupt called reset. The hardware, software and internal interrupts are serviced on a priority basis. The internal interrupts have the highest priority and the external hardware interrupts are the lowest priority group. Also, the various interrupts within a group are numbered 0 to 255 so as to denote 256 interrupts. The lowest number indicates highest priority within a group. Therefore, type 0 has the highest priority and the type 255 has the lowest priority. Few of the interrupt types are not available for the programmers to use as they are used for CPU internal interrupts. For example, divide by 0 exception is a type 0 interrupt generated as an internal interrupt by the CPU. Another interrupt is overflow interrupt which is assigned type 4 in 8088/8086 microprocessor. Type 0 has the highest priority and type 4 interrupt overflow interrupt has the lowest priority. The importance of the priority lies in the fact that if the processor is serving an interrupt at a particular priority level, it can be interrupted by a higher priority device only. The devices connected to higher priority interrupt levels are automatically masked out. Therefore, events like power failure must be linked to highest priority interrupt. As explained earlier, a microprocessor 8088 can handle up to 256 interrupts. A mapping is required which indicates where the program control should be transferred corresponding to the type N of the interrupt. An interrupt pointer table is used to link the interrupt type numbers to the locations of their service routines in the program storage memory. In short, every point corresponds to 4-byte register pair. In the register pair, there are two registers. One is instruction pointer, which is called IP in short. Another register is code segment register called CS in short. These two registers are used for transfer of control to the corresponding subroutine in the microprocessor 8088. Therefore, the first 1 kilobyte of memory is reserved for storing 256 address pointers corresponding to 256 interrupt types. Each address pointer requires 4 bytes of storage and stored at even address boundaries. The higher addressed word of 2-word vector is called base address and identifies the code segment where the service routine resides. The lower addressed 2 bytes indicates the offset of the first instruction of the service from the beginning of the code segment area. The first 5 pointers have dedicated functions. The pointers 0, 1, 3, 4 are required for 8088's internal interrupts. The pointer 2 corresponding to the second entry in the interrupt vector table is used to identify the starting location of the non-maskable interrupt service routine. The pointer 0 is for divide by 0 error, which indicates that program control will be transferred to the address pointer 0 on the occurrence of divide by 0 event. The pointer 1 is for single step mode, which indicates that the microprocessor is set in a single step mode. The interrupt generated after every instruction will transfer the program control to a location corresponding to the address pointer 1. The routine corresponding to pointer 1 is required to facilitate step by step operation of the CPU and allow the user to see the contents of the various registers for better debugging in step by step mode execution. The pointer 3 corresponds to the breakpoint and pointer 4 is used for overflow interrupt. Next is the interrupt instructions of the microprocessor 8088. In an earlier topic on how a CPU executes an instruction, we have explained how CPU executes the instructions. A number of instructions are provided in the instruction set of 8088 for use with interrupt processing. The two instructions STI and CLI permit manipulation of the 8088's internal flag through the software. The STI stands for set interrupt enable flag. The execution of this instruction enables the external interrupt input through the INTR for operation. The CLI, which clears the interrupt enable flag, disables the external interrupt input. It does this by resetting the flag. The next instruction is the software interrupt instruction indicated as INTN. It is used to initiate the software vector call of a subroutine. For example, the execution of the instruction INT25 initiates the execution of the subroutine whose starting point is identified by vector 25 in the interrupt vector table. That means the 8088 reads IP and CS instruction pointer and code segment from addresses in binary 0110, 0100 and 0110, 0110, which corresponds to 100 and 102 respectively. These values are loaded into IP and CS respectively, so that the program control is transferred to these locations. an interrupt return instruction must be written at the end of each interrupt service routine, and the job of the interrupt routine is to return from where the return to the main program after servicing the interrupt service routine. The next instruction is INTO. As the name implies, INTO is an interrupt on overflow instruction. This instruction must be included after arithmetic instructions that can generate an overflow condition, such as addition, subtraction. It tests the overflow flag. If the overflow flag is set, a type 4 internal interrupt is initiated. The overflow service routine is located at the starting address identified by the vector IP4, that means in hexadecimal it is 0010, and CS4 is located at 0012 in hexadecimal of the pointer table. Another interrupt instruction associated included in 8085 are halt and wait. When the halt instruction is executed, the 8088 suspends operation and enters the ideal state. It no longer executes the instruction and remains ideal, waiting for the occurrence of an interrupt event. The next is interrupt masking. An interrupt enable flag is provided in 8088 identified as IF in the status register. It affects only the external hardware interrupts, not the software or internal interrupts. The external hardware interrupt can be interrupted by the CPU only if IF flag is on, else they are disabled. During the initiation of the interrupt service routine, 8088 resets IF flag. This masks out the occurrence of any additional external hardware interrupt. If necessary, the interrupt can be enabled with STI instruction during the start of the ISR so as to re-enable the external hardware interrupt. However, a type of interrupt called non-maskable interrupt is not affected by this flag. The NMI interrupts are used to indicate a catastrophic event like power failure. When this event occurs, the interrupt is treated as the highest priority interrupt and is handled by switching the power supply to an alternate power source like battery. In case of the failure of the alternate power supply too, the NMI saves the current state of the CPU. That means the registers like program counter, status register and all general purpose registers are saved into the memory and initiate a normal shutdown operation so that all open files contents are written properly in the hard disk and the operating system programs are closed properly. An abnormal shutdown can corrupt the operating system and may require a fresh restart of the programs currently under execution. Next is the spurious interrupt, a hardware interrupt that is unwanted. They are typically generated by the system conditions such as electrical interference on an interrupt line or through incorrectly designed hardware. So, what we have learned today can be summarized as what is an interrupt, how it occurs, what happens in the CPU when it receives an interrupt, using the example of microprocessor 8088/8086. The interrupts were explained with the help of interrupt related instructions. Thank you.